Hello. All right. So we've been talking about Fourier series, and the idea is we talk about Fourier series as a way of inverting the CDFT, the continuous to discrete Fourier transform. Thus far, we've been talking about mostly about conditions that initially involve a signal being in L1. And now what we want to do is we want to look at the special structure that arises when signals are in L2. It turns out this is this little move from L1 to L2 gives a lot of additional structure, and some of that is a result of the inner product structure that the norm possesses on L2. And so what we want to do is spend a little bit of time talking about inner product spaces. I could have, and maybe should have, talked about this when I talk about Banach spaces, because this is kind of in that category. But I'm going to do it here. Okay, so and product. And F vector space. V is mapping. Okay, and this mapping takes two vectors in V, let's call them U and V, and it maps it to a scalar. Okay, and of course, this assignment of the scalar U V, like so, should satisfy some conditions. Okay, so the conditions are that if I take the inner product, so the inner product of U and V, and I swap the entries, I don't get the same thing back, but I conjugate it. And so in this special case, when F is equal to R, this is equality without just the conjugation. In that case, it's just the identity. Okay. And there's a linearity condition. Sorry. Like so. So this is linearity with respect to addition and scalar multiplication in the first entry, and you don't quite have linearity in the second entry, at least in the complex case, and we'll talk about that. Okay. If you take the inner product of the same vector with itself, that's non-negative, and then there's a definite condition which says that you get 0 implies that V is equal to 0. Okay, so of course if V is equal to 0, then this thing is equal to 0. That follows from just part 2. So this is the converse. So the only time that this is 0 is when V is equal to 0. Okay. All right. So again, we have this symmetry when the scalar field is R. And what about scalar multiplication in the second entry? Well, in the second entry, okay, so when you swap the entries, you get that. And then by the second property of inner products, this is so and so. Okay, so in the second entry, you don't quite have linearity. You have what's sometimes called sesquilinearity. And so this is linearity in the real case, but in the complex case, not necessarily. All right. All right, so we've seen previously examples of inner product spaces. So in Fn, the standard Euclidean inner product is like so. And you know, there's a choice here about where the conjugate should go. Should it go here or here? And that'll affect these linearity properties. And so what you'll get is if you choose to put the conjugate here, then you're going to get the this kind of property in the first entry and then linearity in the second entry. Okay, and different people do things differently. Basically, if one wanted to characterize who does what, mathematicians do it this way, physicists do it the other way. Okay. Okay, so on the space of L2 sequences, okay, define an inner product like this. So we've looked at these before, so I'm not going to spend a lot of time talking about them. Okay. Okay, and then on function spaces, continuous time function spaces, you get an inner product like that. Okay. All right. Okay, so what about what additional structure does an inner product give you? Well, it gives you a lot of special structure, and for one, inner products give you norms. And I'll state this as a thing like so. So if right, so we have an inner product space. So of course, this just means it's a pair. V and this, where this is a F vector space and this is an inner product, as defined above. And let's define okay, this thing which has a symbol like a norm because it is a norm. Okay, so if we do that, then this is a normed vector space. All right, so let's prove this. This is kind of elementary, but let's do it. Okay, so first, we prove the Cauchy-Schwarz inequality, which is a very important thing all by itself. And the Cauchy-Schwarz inequality says this, that if I take the inner product of u and v, which is going to be a scalar, and I take its absolute value or complex modulus, then this is less than or equal to the product of the norms of the two vectors. Okay, so this is a very important inequality. So let's prove it. Okay. So assume first that the norm of v is equal to 1. Okay. All right, so then, just for simplicity, and then the other case will follow easily from what we proved there. Okay, so then we compute. Okay, so this is kind of just an elementary computation using the property of properties of inner products. Okay, so first thing is okay, that's our kind of starting point of the computation. Okay, so remember that I haven't yet proved that this thing is a norm, but nevertheless it has a definition, and its definition allows me to manipulate things, and so I'm squaring this, and so this is just really the inner product of the thing inside with itself, and so I'm going to expand that using the property of inner products. Okay, and so I get, after doing that expansion, I get V1 with U with itself. Okay, and then I get this scalar is going to come out with the inner product of U and V. So it's U, V. And then here I get VU, is the order in which the scalar comes out like so. Okay. And then I get minus U conjugate UV. All right. And then, so these are sort of the cross terms when I expand this inner product with itself. And then I get the other term, which is so, all right. Okay, so now I notice that this whole business okay, so this is U squared, okay. Then noting that if I switch this around, I'm going to get the conjugate. Then what and then also, oh, sorry, I apologize. I made a typo here. That should be V, sorry, V Okay, and so I'm going to use the fact that the norm, although I haven't proved that it's a norm yet, the norm of v is equal to 1. Okay, and so so the point is that these guys cancel, and this is minus u squared. Okay, so that is what I end up with there. And the point is that this is positive, and so the Cauchy-Schwarz inequality immediately follows from there. Okay, so that gives me Cauchy-Schwarz. Okay, so that's Cauchy-Schwarz when the norm of v is equal to 1. So if norm v is not equal to 1, okay, okay, so the first case to look at when v, the norm of v is not equal to 1 is when v is equal to 0. In that case, the Cauchy-Schwarz inequality holds with equality. Okay, and so let's take this not equal to 0 or 1. Okay, so it's some positive number. Right, and so then v over v is equal to 1. Okay, and then you apply the Cauchy-Schwarz inequality with this vector, because that's what I just proved above, and you get u v over v. So is equal to, sorry, is less than or equal to u like so. Okay, and this is 1, right? And I can take this quantity here, which is just a scalar, and I can pull it outside, and it's positive, it's real actually. And so when I pull it outside by this observation here, because the scalar is real, it'll just pull out without any conjugation, and then I can pull it out outside the absolute value, and then because and so this quantity is non-zero, then I can multiply by it and bring it over to the other side. So the point is, after an elementary manipulation, I get exactly what I want. Okay. All right, so that's the Cauchy-Schwarz inequality in general. Okay, good. So now we're going to use that to prove that the norm that we defined, like so, is a norm. Okay. All right, so to show that this is a norm, the only non-trivial assertion is the triangle inequality. Okay, so the other norm properties, homogeneity and definiteness, follow from the properties of the norm, or sorry, from the properties of the inner product, and so we just have to prove the triangle inequality. Okay, and so this again is just an elementary computation. Okay. Using the keeping, so we're going to calculate the norm. So again, we haven't quite yet showed that this is a norm, but this quantity squared is equal to the inner product of this with itself, and then we're going to expand using the properties of the inner product. Okay. All right. So it's u squared plus uv plus uv conjugate plus squared. Okay. All right. Now what's what's a complex number plus its conjugate? Okay, well, that's going to be 2 times the real part of the complex number. So this is 2 real part of this thing. Right. And so this is going to be now less than or equal to. Okay. The modulus, all right, so this is potentially negative, and so I'm going to replace it with its absolute value and put the inequality in there. So, and then if you think about the definition of all the symbols here, the modulus of the real part is less than or equal to the modulus of the complex number itself. Okay, and so this is equal to sorry, this is where I use Cauchy-Schwarz. Oh, sorry, somehow I started writing V here instead of U. Okay, so by Cauchy-Schwarz, this is and finally, this is that. Okay, and then taking square roots gives you the triangle inequality. Okay, all right, so inner products are norms. Good. Okay, and so Hilbert space is like a Banach space for inner product spaces. Okay, is inner product space for which the associated F norm space is a Banach space. Okay, so it's complete. Every Cauchy sequence converges. Okay. All right. How special are normed, sorry, are inner product spaces in of normed spaces. Okay, so should you think of most norm spaces as being inner product spaces? Very few. Well, very few is the right answer. And in the finite dimensional case, of course, none of these distinctions are, from a certain point of view, material. In finite dimension, the topology of every normed vector space is the same as the topology which comes from some inner product, because every finite dimensional vector space, and in fact, every vector space has an inner product. And so how would you establish an inner product for an arbitrary, well, finite dimensional vector space? Well, you would choose a basis, okay? And then by choosing a basis, you have chosen an isomorphism of that vector space with Fn, and then you can just use the Euclidean inner product, okay? And generally, that's how you put an inner product on an arbitrary vector space, is you choose a basis for the arbitrary vector space, but now the basis, of course, won't be finite. And then you define associated with that an inner product. And we're going to talk about things connected to that a little bit later on, okay? So certainly it's true that every vector space has an inner product, but that does not mean that every normed vector space is an inner product space, okay? So let's explore some facts connected to this question. Okay, so one fact is this, is that a norm on an F vector space comes from an inner product okay? And so by that, just to be clear, I mean this. Okay. If and only if. Okay, there's a simple verification that you can make to test whether a norm comes from an inner product, and it's called the parallelogram law. And the parallelogram law reads like this. Okay. So it's easy to check that if a norm comes from an inner product like so, then this holds. That's a relatively easy check. It's surprisingly complicated to show the converse. So in other words, if this is true, then the norm comes from an inner product. Okay. And so you might want to draw what this means in the plane, for example, for a parallelogram with sides given by u and v. What does the parallelogram law mean? Okay. All right, so you can kind of see where the parallelogram law comes from geometrically, but to actually prove that the holding of the parallelogram law is sufficient for a norm to come from an inner product is quite complicated. All right. Okay, so inner product spaces. So that's one sort of thing connected to my question here about how special are inner product spaces. Okay, so inner product spaces permit the notion of orthogonality that does not make sense for general norms. And so a lot of the speciality of inner product spaces in the class of norm spaces comes from this orthogonality construction. So let's indicate what that means. So we say vectors u and v in an inner product space v are orthogonal if u v is equal to 0. All right, so orthogonality okay, so right, so this would be the standard inner product in Fn. So let's think about just R2. Okay. One can verify that if u and v are non-zero, okay, so obviously if one of them is 0, then they're always orthogonal. So this is really only interesting when they're both non-zero. Okay, so if I fix u, then I know that v must lie somewhere in that one-dimensional subspace, which is perpendicular or orthogonal. That's the 0 vector to u. Okay, so that's where kind of you can get some intuition about what orthogonality means. So we're going to talk quite a little bit about orthogonality. Okay, but let's maybe just for fun think about a question which is kind of related to this notion of orthogonality. So actually, before I sort of do that, let's so we can say that subsets, say A and B in V, are orthogonal if, of course, every pair of vectors from A and B are orthogonal. Okay, so this is particularly interesting. For subspaces. Okay, so let me list some facts that are sort of associated to what I mean there. So if A is a subset of V, then denote a perp to be set of V's in V, which are orthogonal to every point in A. Okay. Okay, so a perp is a subspace. And no matter whether A is a subspace or not, a perp is always a subspace, and that's relatively easy to verify just from that condition. Okay, and in fact, a closed subspace And so what this shows, for example, is that not every subspace is the orthogonal complement of something. Okay, so in finite dimensions, this is a situation where your finite dimensional intuition isn't going to give you any insight, because in finite dimensions, all subspaces are closed. Okay, so this is the statement has only content in the infinite dimensional case. Okay. So a perp is equal to closure of the span of a perp. Okay, so you can take a kind of much larger subset and its orthogonal complement. So I think I didn't define the terminology here. This thing is what's called the orthogonal complement of A. Okay, and so the orthogonal complement of A is the same thing as the orthogonal complement of something which is potentially quite a lot larger than A, namely the closure of the subspace generated by A. Okay. And so if U and V, sorry, U and W are closed subspaces, that are orthogonal, then V is the algebraic sum of U and W. Okay. All right, so so there's some features of orthogonality. So let me ask a question which is rather related to all of this business. Okay. 3. And this is called the complemented subspace problem. Okay. And it's an illustration of the way in which inner product spaces are special. Okay. So we start the discussion by talking about a normed vector space. In fact, a Banach space. Okay. So a question. When is it true that for any closed subspace, U of V, there exists a closed complement? And by that I mean a closed subspace W such that V is U plus W. Okay. All right. So first thing is this is not always true. Okay. So there exist Banach spaces, and the examples are not incredibly pathological, but Banach spaces with closed subspaces that do not have a closed complement. Okay. So the question is, what property should a normed vector space have in order to ensure that every closed subspace has a closed complement? Okay, and so the answer, so this was a problem in Banach space theory for a while, and it was solved in the early 70s by Strauss and Zafiris. I think it was 72. This is true if and only if there exists an inner product giving rise to a complete norm. So in other words, the inner product makes this vector space into a Hilbert space. And the topologies defined by the two norms agree. Okay, so let me say this hopefully more clearly than I just did. So I already have a norm on my vector space. Okay. What I'm saying is that the normed vector space has this complemented subspace property. So every closed subspace has a closed complement, if and only if morally the inner product space is the normed vector space is an inner product space. So in other words, that doesn't mean the norm necessarily itself comes from an inner product, but it means there's another norm coming from an inner product which gives the same topology. Okay, so that's a property of Hilbert spaces in the class of Banach spaces, is that in the class of Banach spaces, it's Hilbert spaces which have this complemented subspace property. Okay. All right. Good. All right, so let's talk about a very special but important feature of inner product spaces in the class of Banach spaces. Okay, so let's talk about orthonormal bases. Okay. All right, so there's a few notions that you have to define. Okay, so let's first start with the elementary things about what I mean by an orthonormal collection of vectors. Okay, so a collection I. So I will be an arbitrary index set here. Could be finite, could be infinitely countable, or it could be uncountable. So vectors in product space V is orthonormal if. Okay, so first, each of these vectors has unit lengths. That's the normal part of orthonormal. All right, and if I take any distinct 2 points in the index set I, let's say I and j, that are well, distinct, then the two vectors ei and ej are orthogonal. Okay, so that's what an orthonormal set is. All right, and so orthonormal sets themselves possess a collection of properties. Let's talk about those. Okay, so I'm going to take an inner product space. And an orthonormal set. Okay. Okay, so the set is maximal. Okay. If it's maximal in the family of orthonormal sets which contain it. Okay, so let me say what that means. So it's maximal if for an orthonormal set, sorry, f fj, okay, for which the e's are contained in the f's, we have that these families of vectors are in fact the same. So this means more or less that you can't add any more orthonormal, any more vectors to E and have it still be an orthonormal family. Okay, that's how to read that definition. So it's maximal with respect to the property of being an orthonormal set. Okay, so set so maximal is total if I take the span of these guys, and then I take the closure of that, that's equal to V. Okay. So this means, you know, the closed subspace generated by these vectors is equal to V. Okay. And then finally, basic. If given a vector V in V, we write V equals some I C I for some C I's in F. Okay, so now it's not entirely clear what this means. Okay. So when we were just doing linear algebra and we were writing expressions like this for bases, the definition in those cases of what we meant by a basis was such that the sum was always finite, okay? Because the set of basis vectors had the spanning property, which meant that every vector in the vector space was a finite linear combination of the vectors from the basis. But here we're not requiring that the sum be finite, and so I need to say what that sum means, especially given that it's an uncountable sum. Okay, so let me talk about that. Okay, so now I need to embark on an aside. Arbitrary. So we need to consider arbitrary sums, normed vector spaces. In general, we're talking here about inner product spaces, but the discussion really is about normed vector spaces. Okay. All right, and so we have already notions of sums, countable sums. Okay, so let's let V be normed vector space, and consider a countable sum to start with, just to get the ball rolling. Okay. Okay, so we're going to talk about various ways in which this sum might converge. Okay. All right, so this, generally the sum is senseless, so we need to say what convergence means. So this sum does not generally converge and indeed there are multiple notions of convergence. Okay, so one. Right, so the series, or the sum, converges, just plain converges, if so it converges to a vector V if for any epsilon exists n such that the kth partial sum for any k larger than n is within epsilon of V. Okay. So V minus the kth partial sum and this is true for any k greater than or equal to n. Okay, so this is kind of the standard notion of convergence that you inherit from a series of real numbers. Okay, and it makes sense for countable sums in normed vector spaces. All right, so the series converges absolutely if the series of norms. So this is now just a series of real numbers, positive real numbers, no less, converges. Okay, so we talked a little bit about this when we talked about, for example, little L1. So what this definition means is it means that the sequence defined by the norms of these vectors, okay, isn't little L1. That's exactly what the convergence of this thing means, because it's a sequence of a series of positive terms, and so it either converges or it diverges to infinity, and I'm saying it converges. Okay, so another way of saying it is that it converges absolutely. And so for a positive series of positive real numbers, convergence is equivalent to absolute convergence, but it's not true for general series of real numbers, but possibly also negative, because you can have as we talked about, you can have things like some j equals 1 to n minus 1 to the n over n. Sorry, that should be a j, but anyway, the alternating series, which converges in this sense, but does not converge absolutely. Okay, so there's absolute convergence. And then, but these two notions of convergence are not helpful for defining what it might mean for an arbitrary series to converge. Okay, so by an arbitrary series, I mean a series with an index set that's not necessarily countable. Okay, all right. The series converges unconditionally if for any bijection sigma of the index set, which is countable in this case, okay, the series, all right, so the relabeled series converges. Okay, so this means convergence in the usual sense. So no matter how you relabel the set, the series still converges. It might not converge to the same value, but it converges. Okay. It'll converge to the same value if it converges absolutely. Okay, so now one of the things that we know is that for series of real numbers, okay, so when the vector space is the vector space R, and in fact for any finite dimensional vector space, it is also true that absolute convergence is the same thing as unconditional convergence, okay, and both of those generally differ from convergence, okay. Now we're not working here with finite dimensional vector spaces, we're working with infinite dimensional normed vector spaces. Okay, so in those cases, what are the relationships between these three notions of convergence? Okay, right. So if V is finite dimensional, we have unconditional conditional convergence implies, well, is in fact equal to absolute convergence. And these both imply convergence. Okay, and the converse does not generally hold. Okay, now what about in infinite dimensions? So if V is infinite dimensional, we have, okay, right, so which one do you expect is stronger? Well, it turns out absolute convergence is the stronger kind of convergence. And so you have absolute convergence implies unconditional convergence. Implies convergence. And generally, the converses to these implications do not hold. Okay, and so one of the conclusions of this is that unconditional and absolute convergence agree if and only if V is finite dimensional. Okay, so that's not an easy statement, and so the assertion of this is due to Dvoretsky and Rogers. Okay. Right, so it's kind of a major theorem to prove that in an infinite dimensional normed vector space, and I think it actually needs to be a Banach space, generally speaking, unconditional convergence does not imply absolute convergence. Okay. How does this help us in answering the question of what does arbitrary the convergence of an arbitrary sum like this mean? Well, so can these notions, which of these notions can be adapted to arbitrary sums in normed vector spaces? Well, this one clearly cannot. This is a very countable kind of a construction because it relies very much on the order of the index set, right? So we're using the order of the index set here. So this one's, you're not going to have much success with this one in terms of talking about convergence of arbitrary sums. What about this one? Well, this one's okay, right? Because I take my arbitrary family of vectors, VI, let's say, for an arbitrary index set I, and then I can form this infinite series of numbers, and it makes sense to ask when that infinite series of numbers converges. So it'll be an arbitrary sum, okay, an arbitrary sum of positive numbers. And so, but it still makes sense to talk about convergence of that. And really that just means that, it doesn't blow up to infinity, okay? And so we'll see how to do that, okay? And then also we can come up with a restatement of this definition of unconditional convergence, which actually makes sense for arbitrary sums. Okay. All right, so I'm still working on my side here. All right, so now consider an arbitrary sum. And so the point is that I have an arbitrary index set I. Okay, so we say that this series converges unconditionally if, well, to V, if so sorry, I think I didn't say this carefully. This converges unconditionally to V. And yeah, in fact, I think I just said something wrong previously. Sorry about that. To V. Okay, so yeah, so the point is that this sum has to converge to V for any rearrangement. That's what unconditional convergence means. Apologies. Okay, good. So this series converges unconditionally to V if given an epsilon positive, there exists a finite subset such that the difference between the finite sum over the vectors in F and the vector V that you're talking about is less than epsilon. Okay. All right. All right, so that is unconditional convergence. All right. So yeah, sorry. Okay, so you want to mimic kind of what's going on here, and so we talked about finite sums over sets F prime, and the set F prime should be larger than F. Like this. Okay, so that's how you kind of mimic the for k greater than n business. Okay, all right. So so there's a some finite set, and so this is like some capital N. So that if I sum over any finite set which contains F, the result is with an epsilon of V. Right. So that's unconditional convergence, and the fact for countable sums. So I have two competing notions of unconditional convergence now, and in fact they're the same. So for countable series sums, the two notions of unconditional convergence agree. Okay. All right, so this one involving finite subsets and this one involving rearrangements. Okay. All right, and the advantage of this one is that it makes sense for arbitrary sums. Okay, and that's kind of the whole point. And so notice that arising from this is if I apply my observations here for finite dimensional series, I have that unconditional convergence is equivalent to absolute convergence. And so I can therefore say I can make sense of absolute convergence of a series since, okay, so first of all, by asking that, so the obvious notion of absolute convergence would be requiring that this converge. Okay, and why does this make sense? It makes sense because of the agreement of absolute and conditional convergence in finite dimensions. Okay, so let me clarify. Okay, so I have a series like this, an arbitrary series in a normed vector space. Okay, and I'm going to say that it converges absolutely if that's true. Okay, now how does that what do I mean by convergence of this arbitrary infinite series of numbers? Well, what I mean is I'm going to define that to mean, you can define it just by asking that it be, that it converge and then think about what that means, or you can just take note of the fact that, like I said, absolute and unconditional convergence agree, and so really the convergence of this can be taken in this sense, okay, but where I'm now talking about a series of positive real numbers. Okay, so I'm applying this definition of unconditional convergence to a series of positive real numbers, and that makes sense because absolute and unconditional convergence agree in that case. Okay, and so the point is that this new definition of absolute convergence agrees with the countable definition of absolute convergence. Okay. Okay, good. So I have and just like here, it's generally going to be the case that absolute convergence will be a stronger notion than unconditional convergence. Okay. All right. And okay. So this ends my aside. Okay. And now, why did I make that aside? I made that aside because in this definition of basic, I wrote this weird arbitrary sum. And so now I should say what this means. Okay. Okay, so this means unconditional convergence. Okay. All right, so that was the whole point of this digression about series in normed vector spaces, so that I could make sense of what this sum actually means. Okay. All right, good. So now we have these various notions for families of vectors in inner product spaces. How do they relate to one another? Okay. All right, so to explore that, there's two basic facts about these kinds of infinite series. Okay, so facts. Okay. All right, so let's let V be product space. All right. Okay. So the first thing is if, oh, sorry. And that EI be an orthonormal set. Then, if V is sum I equals 1, 2, sorry, I in I, C, I, E, I. Okay. Then, okay, CI must equal the inner product of V with EI. Oops. Okay, so that must be true. So one of the consequences of this, by the way, is that if the series converges, then it turns out that only finitely many, sorry, countably many of these coefficients CI can be non-zero. And so what that means is that V is going to be orthogonal to some countable collection of these EIs. Okay, so in the uncountable case, the sum is still countable. So that's another fact that is lying in the background here. Okay. And the other useful fact, so you know, this is a formula that you, if you've studied elementary inner product spaces, that you will be familiar with. And in the finite dimensional case, this is obtained just by direct calculation, right? So you just take the inner product of V with each of these E's, and then you just use this finite sum, and out pops that condition, okay? But the fact of the matter is that holds for even uncountable sums. Okay, good. This is a thing we've used previously. and it kind of underlies a lot of the stuff that follows. And it says this, if V is in V, then okay, no matter what. So I'm not, for example, requiring this hold. Okay, I'm just taking any V and any orthonormal set. Doesn't have to be maximal or total or basic. This holds. Okay. All right. So this is a Bessel's inequality. Okay, good. Now, using these things, we can prove some relationships. We're not going to prove this, but I'm just saying that if we were to write all this stuff out, which we're not going to do, you can use these facts to prove the following result. Okay. So let V be an inner product space and let EI be an orthonormal set. Okay. Then the following statements are equivalent. Okay, so let me just abbreviate this so I don't have to write that constantly. B is basic. B is total. Okay, so basic means, remember that every vector can be written as an infinite linear sum like so. Okay, and total means that the closure of the subspace spanned by the E's is V. Okay, so those things are equivalent, and there's other things that are equivalent too. Okay. Okay, so one is that Bessel's inequality is equality. So the sum I V E I squared is equal to V squared. Another, which is again equivalent to the previous three, is that the inner product. All right, so this is a formula for the norm of V. The next thing, and so I should be clear here, this is true for every V in V. And so the fourth condition is for the inner product of two vectors, U and V. Okay, so it's U E I V E I, like that. Okay. All right, so if you write again U or V like this, okay, and then write U and V in an expansion like this, where the CIs are by this fact given by this, and then sort of just expand out the inner product naively, forgetting about convergence of sums or anything like that, then this is the formula that you'll get. Okay, but the fact is that formula is true when you do worry about convergence of sums, right? Okay, all right. Right, and so what does convergence of this sum here mean? This is an arbitrary sum, so this means unconditional convergence is what I mean by that. Okay. And similarly here, these are unconditionally convergent. Okay. And in this case, of course, because these are positive, that's the same as absolute convergence. Okay, but in this case, well, sorry, actually, in this case, this also means absolute convergence because these are scalars. And so absolute convergence and unconditional convergence agree for scalars. Okay, good. All right, so additionally, the following, so let me just sort of, okay, so I have two groups of equivalent statements, one group of 4 and then another group of 2. Okay, so the other pair of equivalent statements is the only vector orthogonal to every vector in the orthonormal set B is 0, and that is equivalent to maximality in general. Okay, and then finally, if B is Hilbert space, all 6 statements are equivalent. Okay. All right, so this is a big theorem which sort of asserts a lot of things. A lot of them are useful when we come to talk about Fourier series. Okay, and so the proof of this is not so hard. There's a lot of stuff to do here, and so it requires some work, but it relies heavily on Bessel's inequality and basic things about orthogonality. Okay. So it's not hard, but tedious. All right. So with these notions in mind, let's make a definition. And that'll be the last thing we do today, and we'll continue talking about this next time. All right, so the definition is going to be for your product space. Okay, a Hilbert basis is a maximal orthonormal set. Okay, and so let's maybe think about how this is the same and how it's different from our previous notion of a basis. Okay, so the way in which the two notions are comparable is through this notion of maximality. Okay, so how should you think about a basis? Well, a basis should be thought of as being a maximal linearly independent set. Okay, so in other words, if it's maximal in the sense that if you take any linearly independent set which contains your set, then it's actually equal to it. Okay, so there's no linearly independent set that's larger. So that's the normal notion of a basis. And so a Hilbert basis is the same idea in the family of orthonormal sets, not just linearly independent sets. So orthonormal sets are certainly linearly independent. You might want to verify that yourself. But they have many more properties than just linear independence. And a Hilbert basis is maximal in that collection of things. And so notice that in a Hilbert space, right? So in Hilbert space, maximal is the same thing as basic. And so in a Hilbert space, basic means, oops, where am I? Right here, okay? So if this set is a Hilbert basis, then this means because a basic orthonormal set is the same thing as a Hilbert basis in a Hilbert space, then in a Hilbert space, it means with a Hilbert basis, it means every vector can be written like this. And this is the big difference between Hilbert bases and ordinary bases, is that an ordinary basis, when you write a vector as a linear combination of the basis elements like so, that linear combination is finite. That's the definition of a basis. But for a Hilbert basis, this sum is not finite. Okay, so that's, so you need to talk about convergence, and so you need all the structure of a norm, which comes from the inner product, to be able to make sense of that. Okay, all right, so what we will do next time is we will talk about a few more things about inner product spaces, and then we'll see how this impacts our discussion of the CDFT and Fourier series.